Hello! In this series of videos, we're going to take a look at particles and potential steps. So, truly infinite potentials, which I discussed in the previous series, are hard to come by. In this series of videos, we're going to look at some real-world examples where the potential is set to some potential V0, but not infinity. Okay? For example, let's take a look at this diagram. The particle, okay, as we have here, is in a region where V is equal to 0, okay? So there's no potential. But it will soon be in the region where V is equal to V0, okay? It's travelling to the right. Alright? So, there are two cases to look at here in terms of E, which is the energy of the particle, okay? So, the first case is where E, the energy of the particle, is greater than V0. Okay? Classically, when the energy is greater than V0, you expect the particle to be able to continue onto the region x is greater than 0. Okay? Because it has enough energy to overcome the potential step. Okay, and the second case is where the energy is less than V0, okay, and of course you would expect the particle to bounce back and not be able to get to the region x is greater than 0 at all, okay? So first of all, in the first couple of videos, we're going to start taking a look at the case where the particle's energy, E, is greater than the potential V0, okay, as shown in this diagram. Okay, and then, of course, we're going to look at 2, where the energy is less than V0. Okay. So we're going to start where the case the particle's energy is E is greater than the potential V0. From a quantum physics point of view, here's what the Schrödinger equation looks like. So, when x is less than 0, okay, if you haven't seen the videos on the square well, the particle in the infinite square well, we derived the Schrödinger equation, the wave function for that. So if you're not familiar with this, you might want to go and check that. But if you have seen the videos, you'll be familiar with the Schrödinger equation, which we have here. Okay, so as you can see, we have K1, okay, and we have the first wave function, psi1, and of course that's equal to 2me divided by h bar squared, okay, and that's where x is less than 0, okay, where the potential is 0. That's where the particle starts. Then, when x is greater than 0, we have this differential equation, psi2 and k2. Now, k2 is equal to 2m multiplied by the difference of the energy's particle and the potential divided by h bar squared, okay, so there's a difference. Okay, so the second differential equation, okay, applies to this region where x is greater than 0, okay? So as the particle comes in, we have, of course, when x is less than 0, we just have the region E. So k is just going to be 2me over h bar squared. However, when it comes into this second region, x is greater than 0, we're going to have to take a difference between the energy and the potential V0. Okay, so there are two cases, or two different Schrödinger wave equations. Okay? Right. So, in other words, because k is of course different in both cases, they're going to vary by region. Okay, and I've shown this by rough graph. We have K1, so this region is where x is less than 0. This region is where x is greater than 0. As you can see, K1 and K2 vary between the regions. Okay, so treating the first equation as a second order differential equation, you can see that the most general solution is the following. So where x is less than 0, okay, you'll be familiar with this already, but we have psi1x is equal to, okay, we're going to write it in terms of E, so we have a e to the I k1 x plus b e to the minus I k 1x, like so. Okay, that's for where x is less than 0. So we're looking at that differential equation here. Okay, and of course we have our solution where x is greater than 0. Okay, where x is greater than 0, you could probably do this yourself now, but we're going to have psi 2 of x is equal to c, okay, these are just constants, the letters, e to the I k2x, and then we add d e to the minus I k2x, like so. Alright, now, we're just going to do a note here. So e to the I kx represents a wave travelling in the positive x direction, and e to the minus kix represents plane waves travelling in the negative x direction. Okay? Right. So, what this solution means is that the waves can hit the potential step from either left, okay, from left, and be either transmitted or reflected. So given that way of looking at the problem, you may note that the wave can be reflected only going to the right, not to the left. So d must equal 0. So we're going to get rid of d. That has to be 0. Okay, so that whole thing becomes 0. So you can think of it as this. So in term, this a e to the I k1x represents the incident wave, okay? This represents the reflective wave because it's coming to the left, right? Negative, okay? And of course, this represents the transmitted wave. So I'm going to get the diagram again. So psi